Hello and welcome to topic 1.3, reacting masses and volume. This is part number 3, so we're going to focus on gases and the gas laws. First, we're going to take a look into the syllabus. This is the understandings and the application skills that are in focus for this part of this subtopic. We're going to look at different gas laws, and there are kind of few. There are many, so we're going to look at the relationship when we have pressure, temperature and volume. We're also going to look at the molar concentration and some different gas laws. So this is the syllabus, and I have tried to organize it so it gets more clear for you. So overview is that these are the different gas laws that we're going to get through one by one, and I'm going to give you some examples. The different gas laws that we have here will help us to understand the relationship between the pressure, volume and the temperature. So if we combine what we call is Boyle's, Charles and Gay-Lussac's law, together they will create what we call a combined gas law. And that is when we can see the relationship between pressure, volume and temperature. If we later then add the Avogadro's law to this one, we can have something that is called the ideal gas equation. So this is something I will show you, but before we do that, I have some additional information. The first thing is the chemistry data booklet. There are some good information, so it's good to know where you can find it. So if you go to section number 2, here you can find, for example, STP and SATP. The STP stands for standard temperature pressure, and that is when we have 0 degrees or 273 Kelvin degrees and 100 kilopascal. So this is the pressure and this is the temperature. Then we have something called SATP conditions, and that is when we have 25 degrees and 100 kilopascal. So it's the same pressure, but we have room temperature instead. Also here you can find the gas constant, we'll use that later, and also the molar volume of an ideal gas at STP. So you have different given values here, and this is where we can find them. Section number 2 in the chemistry data booklet. Another thing I want to go through is equation that can be good to know, and that is that the N, the number of moles of a gas, is the volume divided by the molar volume. And you can also see that in the units. So if you take mole is equal to cubic decimeter divided by the cubic decimeter divided by the mole. And then you can find out the moles. Yes, so this was also, we'll come back to this later. The first exercise here is this one. In this case you have mercury, and that will have a mercury oxide compound, and it will create mercury in liquid state and oxygen. And in this case they want to know the volume of the oxygen that is released at STP when we heat up 12.45 grams of HGO. So in this case we know the mass, that is 12.45, says here in the task. The molar mass, we can find it easily in the periodic table. So you go to section number 6 in your chemistry data booklet and find both mercury and oxygen and add them together. We have mercury here, so the molar mass for mercury is 200.59 and oxygen has 16, so we need to add them together. And that will give us a sum of 216.59 gram per mole. And now you can calculate the amount of substance, because with this equation you can see that amount of substance is the mass divided by the molar mass. So you take 12.45, divide that with 216.59, and that will give us an amount of substance for the HGO of 0.057 mole. You can put that on your calculator if you want to. What you then do is that you use the mole ratio. You can see that 2 mole of the mercury here is equivalent to 1 mole of oxygen in this equivalence here. You have, this is what you know, this is what you want to know, 2 to 1, and then you divide this by 2, and you need to divide this also. So for every mole of the mercury oxide compound, we can see that we have a half mole of the oxygen gas. So the N for O2 is 0.057 times 0.5. That is 0.028 mole. Then we use the equation I just showed you, where we have the amount of substance is the volume divided by the molar volume. And we know that the molar volume at the standard temperature pressure, because we have the STP condition here, you go to your chemistry data booklet, section number 2. So what is the molar volume for STP? Well, it's 22.7 cubic decimeter per mole. I prefer to use cubic decimeter because we have liters in chemistry, so this is the one I will use now. So the molar volume at STP is 22.7 cubic decimeter per mole, like that. The volume is what you want to know. You want to know the volume. So you have the molar volume, you have the amount of substance. So the volume is the amount of substance times the molar volume. So it's 0.028 times 22.7. So the volume for the oxygen, you just multiply these two numbers. So if we take the GDC here, and that will give us 0.64 cubic decimeter or liter. So this is how you can use the equation and the stoichiometry you have used before in the class. So we're going to continue now. We're going to look at the properties of gases. There are some common properties of gases that can be good to know. One is that they don't have any definite shape or volume. Another way we can know it's a gas is because it's very easily compressed, and also it has a high rate of diffusion. So this is some of the properties we can expect from gases. We also know that the gas particles will exert pressure on the surroundings, because gas is something, even if you can't see it. So this is some of the normal properties of gases. Another thing I want to have with you is also the calculations we are going to do soon, and that is when it comes to temperature. The unit you need to use for temperature to get it correctly, and that is due to the unit we have in the constants, is Kelvin degrees. So if it's given in Celsius degrees, you need to convert it into Kelvin degrees, and you simply just add 273 to the Celsius degrees to get it in Kelvin degrees. And that is because 0 Kelvin is from the absolute 0 point, and that is when we have it so cold that not even particles can move anymore. So now we're going to start with the first law, and that is the Boyle's law. Robert Boyle is the first law I'm going to show you, and what he did was he looked at the relationship between the pressure and the volume. So this is the equation. You will take the pressure for one volume, pressure for one gas and the volume for that, so that is the gas number 1, is equal to P2 and V2. So we're going to start with Boyle's law now. Write up this equation and put in mind that the Boyle's law is the relationship between pressure and volume. Yes, so the exercise here, if the pressure of a helium gas in a balloon has the volume of 4 liter as 210 kilopascal, so this is the volume and this is the pressure, what will be the pressure when you have volume at 2.5? So you will actually decrease the volume and you can expect the pressure to be something else. Probably bigger, right? Because if you decrease the volume and you have the same amount of particles, then you can say that the pressure will increase. So this is what you have from the beginning, and this is what you have in the end. So this is the V1, and this is the P1, and this is the V2. So if I just write up the equation again, P1 times V1 is P2 times V2. What you want to find is the P2 value. So P1 is 210, and then you have this one here. And that is 4. You don't know P2, so you just let that unsaid. P2 you know, that is 2.5. Now you can solve out P2 by divide this by 2.5 and this by 2.5, that will cancel out. P2 is 210 times 4 divided by 2.5, and that will give us 340 kilopascal. Like this. So that was the result for the exercise when we look at the Boyle's law. The next law you need to focus on is the Charles law. And Charles' law will focus on the volume and temperature instead. In this case, we have the V1, that is for the first one, is divided by temperature for the first one, and that is equal to if you have for the second one, V2 and T2. One thing you need to have in mind here is that the temperature needs to be converted into Kelvin degrees. So if it's given in Celsius degrees, don't forget to convert it back to the Kelvin degrees. So yes, we go on with the exercise here. V1, T1, V2, T2. In this case you can see that a gas sample of 40 degrees occupies a volume of 2.32. The temperature is increasing to 75 Celsius degrees, and what will be the final volume? The first thing you need to do now is just to state the different one here and what you know and what you want to know. V1, so this is the first here, you have volume that is 2.32 cubic decimeter. The temperature from the beginning was 40 degrees Celsius, so you need to add 273 to get it to Kelvin degrees. That will give us 313 Kelvin degrees. The V2 is what you seek. They want to know the final volume, but the T2 is given because you increase it to 75 degrees Celsius, and that will give us 348 Kelvin degrees. So now you just put these values into the equation. 2.32 divided by 313 equal to V2, 348, and you know that this one times this one is equal to this one. So V2 is 2.32 divided by 313 times 348. So that will give us 2.58 cubic decimeter. So this is how you use the Charles law, and in this case we're looking at the relationship between the volume and temperature. Next law is Gay-Lussac's law, and the Gay-Lussac's law look at the relationship between the pressure and temperature, and we can see that the P1, the pressure for the first one, is divided by the temperature for the first one is equal to the pressure for the second one divided by the temperature for the second one. Same thing here. Temperature needs to be in Kelvin degrees. Really important. So it's the same thinking here. In this case you have atmospheric pressure, but you can actually have the same number for that one. It's no problem. The pressure of a gas in a tank is 3.2 atmospheric pressure at 22 Celsius degrees. The temperature will rise to 60 Celsius degrees. What will be the pressure in the tank? So once again, the equation looks like this. Yes, so the P1 was 3.2 atm. The temperature is 22 Celsius degrees. You need to convert that to Kelvin, so we add 273, and that will give us 295 Kelvin degrees. The P2 is what we want to know, so that is a question mark, but we know that the temperature was 60 degrees. So you need to add to get the Kelvin, and that will give us 333 Kelvin degrees. So now we put these values into the equation. So P2 is 3.2 divided by 295 times 333. So the pressure in the N will be, if you put that in your calculator, to 3.6 atm. So that was Guy-Lussac's law when we look at the relationship between the pressure and the temperature. So, as I said in the beginning, you can combine these three laws I just showed you to get the combined gas law. And then we have all of these three parameters. We have the pressure, we have the volume, and we have the temperature. And this is the equation for the combined gas law. It says that the pressure for the one times the volume of the one is divided by the temperature. So you have multiplication between the pressure and volume divided by temperature. And then you have the second one on this side of the equation here. So you can be given 5 knowns and you need to solve the one unknown. I will show you an example. We can start by just state the equation again. P1 times V1 divided by T1 is equal to P2 V2 T2. Okay, here it says that a gas have 110 kilopascal and 30 degrees, and the volume is 2 liter. We will increase the temperature to 80 degrees, and that will influence the pressure to increase to 440 kilopascal. What will be the new volume? Well, we have P1, V1, T1, P2, V2 and T2. We have some information in the question here. We can just state that. We have 110 kilopascal from the beginning. We have 30 degrees of Celsius. We need to add 273. So that will give us 303 Kelvin degrees. Oh, I'm sorry, this was the T1. And V1 was 2 cubic decimeter, like this. The pressure will be increased to 440 kilopascal. The volume is what we want to know, so that is a question mark. And we know that the temperature was rising to 80 degrees. So we need to add 273. And that is 353 Kelvin degrees. Now we just put the values into the equation here. One thing can be to have it in one line is that this times this is equal to that one. You can also calculate this one here, and you will get that to 0.73 times this one is equal to 440 times V2, and then you can just divide with this one, and that will give us, this will clear out, then you will just put that on the calculator, and that will give us 0.58 cubic decimeter. So this is the equation for combined gas laws, and this is how you need to use it. Same as always, you need to convert the temperature to Kelvin degrees, never forget that. So this is the combined gas laws when we add these three. I'm now going to show you the fourth Avogadro's law. This is the fourth gas law, and we will first work with that so we can add it to the ideal gas equation. Avogadro's hypothesis states that the equal volumes of different gases contain equal numbers of particles at the same temperature and pressure. So this means that if you are given gas volumes and asked for gas volumes at the same condition, you can find the answer using the mole ratios. So this is what we're going to do. We're going to apply the Avogadro's law. And this is the exercise. 40 cubic centimeter or milliliter of carbon monoxide is reacting with 20 cubic centimeter of oxygen. And this is the reaction here. And they want to know what the volume is of the carbon dioxide that are produced. So we know we have 40 of this and 20 of this, and they want to know this one here. So in this case we can use the Avogadro's law, and that is that we just state the mole ratio. We can see that 2 mole of carbon monoxide is equal to 1 mole of oxygen, that is equal to 2 mole of carbon dioxide. We know we have 40 of this, and we know we have 20 of this. We want to know this one. Well, we can see that we have a 2-to-2 relationship between these two, or a 1-to-1. So we have the same mole ratio between these two. It means that if we have 40 of this, we have 40 of this. So the volume for CO2 is actually also 40 cubic centimeter. So this is Avogadro's law. Now we're going to put that in together with the combined gas law, and that will give us the ideal gas equation. I will just state what it is and how we can use it. So based on the previous laws, we have 4 different factors. We have the volume, pressure, and Kelvin. That was the Gay-Lussac, Charles, and the other one. And also we have now applied the Avogadro's law. And if we merge these 4 together, this is the equation that we will have. PV is nRT. Pressure, volume, amount of substance, gas constant, and temperature. The gas constant R is something you can find in your chemistry data booklet, section number 2. Here you have it. So this is a constant that you can use. And in this case we'll use this one because we have Pascal. You must also use the correct unit when you use the ideal gas equation. The pressure needs to be in Pascal, and the volume must be in cubic meter, and temperature needs to be in Kelvin. So beware of the units here. So pressure in Pascal, volume in cubic meter, and temperature in Kelvin. Important. So, an exercise of this. What volume will 25 grams of oxygen occupy when we have 20 degrees and a pressure of 89,166 Pascal? This is the equation, PV nRT. The pressure needs to be in kilopascal. Oh no, just in Pascal. So the pressure is 89,166 Pascal. The volume the next part here. That is what we want to know. We don't know it, but we know that the answer have to be in cubic meter. Next part is the amount of substance. Well, to make that happen, we need to calculate it from the mass here. We have the mass of oxygen gas to 25 grams. The molar mass, you can find it in periodic table, 16 for each oxygen, we have 2 of them, so 32 gram per mole. And then we have the amount of substance that we can calculate from this equation. So the mass divided by the molar mass, 25 divided by 32. If you put that in your calculator, you will get 0.78 mole. So now we have stated the amount of substance here. We go continue the equation. R was a constant of 8.31 cubic meter per Pascal per Kelvin degrees per mole. So this is why we need to have this. You can look actually for the gas constant if you're not sure. Well, this is not given for you here, but the unit for the gas constant is cubic meter per Pascal per Kelvin per mole. So that is why we need to have this in cubic meter, this in Pascal, and also what we need, the temperature to Kelvin degrees. We know it's 20 Celsius, we need to add 273, so that's 293 Kelvin degrees. Okay, now we have stated everything we need to know, so we can just take the equation. P was 89,166 times the volume. We don't know that. That is what we want to know. Amount of substance was 0.78. The R, the gas constant, on 8.31, and the temperature 293. So we just make this a little bit better here. And you can just put this in on your calculator, and that will give us 0.0213 cubic meter. My recommendation to get it more so you can imagine it is to convert it to cubic decimeter. And 123, that's 21.3 cubic decimeter or liter. Yes, the final thing I want to just show you is how you can calculate the molar mass of a gas. And this is the equation. You take the molar mass of a gas, that is the density times the gas constant times the temperature divided by the pressure. So write this equation if you haven't done it, and I will show you the first example here. Okay, we have a 2.1 liters vessel, and that contains 4.65 grams of a gas. And we know that the pressure is 101,325 Pascal, and that the temperature is 27 Celsius degrees. We now want to know the molar mass for the gas. I will write the equation again. We know something here. We know the gas constant, the temperature, and the pressure is given. The density is the gram per cubic meter. And we know the volume and we know the grams. We can actually calculate that. So the density is the mass divided by the volume. One thing more is that we need to convert it to correct units. We know the volume here. We can just state what we know. The R is 8.31 cubic meter per Pascal and Kelvin and mole. We know the temperature, 27 plus 273, that's 300 Kelvin degrees. The volume is 2.1 cubic decimeter. We want it in cubic meters, so we need to divide it by 1000. Will give us 0.0021 cubic meter. Yes, and the pressure is given 101,325 Pascal. What we don't know directly is the density, but it's easy to find by just divide the grams here, the mass, with this one, but you need to convert it into cubic meter. So the D is 4.65 divided by 0.0021. And that will give us 2214.28 gram per cubic meter. So now we have all this given. Now you put that into the equation to get the molar mass for the gas. And the molar mass will be, when you put that in the calculator, to 54.5 gram per mole. This final thing is actually something we will do in lab also, so you will practice this in a practical way also to get some hint of how to use it. So this was the third part of topic 1.3, the different gas laws and calculations. Thank you for watching.